trends in deep learning models and use that opportunity to walk with you through their history of deep learning and see what kind of models we've started with, what kind of models we are trying to train today, and try to also kind of hypothesize what kind of models we might be able to train tomorrow. As Paolo mentioned, I've spent many exciting years working side by side with both Dan and Paolo at Hewlett Packard Labs. We are mostly responsible for machine learning applications in computer vision and natural language processing. And towards later years, became more and more familiar with the hardware aspects of the deep learning, machine learning world. And my group worked understanding the requirements for the hardware driven by different analytics and deep learning applications. So we looked at different algorithms and tried to understand what kind of memory, computation, bandwidth, and other type of requirements those algorithms impose on the hardware, and what might be the best hardware to build to run those algorithms as fast as possible. And I'm doing pretty much the same right now with Cerebras. So also looking at different deep learning models and trying to map them in a most efficient way into new hardware. So I joined this hottest startup because when I first heard that their pitch, what they were building and the properties of the hardware matched directly my understanding of what's needed to run and to train deep learning models faster. So let's dive in and talk a bit about deep learning models and some applications for hardware from those. So we all know that AI has massive potential. Essentially, we've been lucky to witness unbelievable progress of deep learning over the past several years. It completely changed the landscape in so many domains. And like I also used to teach computer vision course back in Russia several years ago. And recently my ex-colleagues reached out to me and asked to update the course. And I was looking at my old materials and understood that roughly 80% of that is not relevant anymore. And the course was taught like in 2008 before deep learning becomes so prominent. So we need to change how we do things and we need to adapt. But we also know that artificial intelligence is very compute limited today. So we continue to build larger and larger machines, Cerebras included. And it's not only the size of the compute, but we also believe that the properties of the processors should be different. So we need to build a specialized hardware for deep learning. And if we care to admit or not, essentially the processors which we have today, they shape what types of models the researchers are working on. I think one very good example is in the latest year, became prevalent new optimization algorithms, which allow you to train with extreme batch sizes. This is a necessity rather than wish of those researchers, because in order to distribute your training across large number of systems, you're forced to train with a very large batch size, and otherwise their existing hardware won't be utilized properly. So we come up with ideas how to do that. And there are many other examples of models which are kind of designed having the architecture of current processors in mind. So we are looking into how to change those processors and what types of models might become possible when you have a new hardware available to you. And just to tell you that I'm not alone, I'm citing Jan LeCun from his keynote in conference in 2019. So he mentioned that historically progress in neural networks and deep learning research has been greatly influenced by the available hardware and software tools. And it's very true. Another example, I still remember that reading a paper about GNMT, one of the machine translation models, back in 2016, I was amazed to see a note, an explanation why researchers choose that specific topology of the model, because they wanted to distribute the training across several GPUs. And that tweak, that specific feature of the model which they choose, was because it enabled them to do so. It didn't make much sense from the machine learning perspective. They believe that changing it might lead to higher quality of the model, but in order to leverage distributed training, they designed the model as they did. So to me, it was also a sign that something is wrong, and we need to look into what other hardware can be brought up in order to enable us to build more efficient models. And another quote from the same source, that hardware capabilities and software tools both motivate and limit the type of ideas that AI researchers will imagine and will allow themselves to pursue. The tools at our disposal fashion our thoughts more than we care to admit. That's exactly so. I completely agree with this quote. And bear with me one more quote. Is deep learning hardware really necessary? The answer is resounding yes. And one interesting property of deep learning systems is that the larger we make them, the better they seem to work. So today we'll talk a little bit about deep learning specific hardware, and that last comment about the larger we make them, the better they seem to work. This is especially applicable to the recent natural language processing models, which can be trained in a self-supervised manner. That means that you don't need labeled data for that. And that resulted in a blow up of the model sizes. And right now we are training humongous models, and it looks like there is no ceiling for that people try to continue to increase the size of the models and see still improving results. But that rate over parameter count is not sustainable. So on the note of this deep learning specific hardware, the Cerebras has been found especially to do so, to build deep learning specific hardware. The company has been founded in 2016. We have quite visionary leadership. So the company founded by folks who designed chips in the past. We are backed and funded by a quite nice row of venture capitalists and some of the industry luminaries, specifically who knows well the field of deep learning. And we have a very good team. So we have a very engineering focused team. So probably 99% of the team are engineers, either hardware engineers, software engineers, or machine learning researchers. So we have a really strong team to make that happen and to build the hardware and also the software which will run on that software, on that hardware. So what essentially we build, probably heard, we do wafer scale chips. This is our first chip. We call it Cerebras Wafer Scale Engine, or WISE. It is the largest single silicon processor chip built in production as of today. And it packages on this single piece of silicon 400,000 AI optimized cores. And we typically talk about the scale of the chip, but what I would like to focus today is also on how those cores are optimized for deep learning and why we believe that having those special cores will pay off in the future. So the chip has 18 gigabytes of on-chip memory. That means that it's all SRAM and it's all one cycle away from functional units, which will do mathematical operations on that data. And because all of that memory is on chip on the same piece of silicon, it's all SRAM, we have enormous bandwidth, enormous memory bandwidth. And we also have very tight connection, high bandwidth and low latency connection between all of those 400,000 cores. That enables us to apply different distribution techniques across all of those 400,000 cores and seamlessly use a hybrid model of data parallel training, model parallel training, and layer pipeline training. So essentially, we can use all the levels, all available to us degrees of parallelism in deep learning very seamlessly. And for a specific model, decide what's the best way to utilize that parallelism. How much do we want to distribute it across different data points? How much we want to distribute that across model parameters? And that will be chosen based on the model structure and without taking into account any communication constraints, because we don't have communication constraints on the chip, because all the cores sits on the same silicon and very tightly connected to each other. So the first generation of the chip was built with by TSMC using 16 nanometer process. Recently, we've announced the second generation, so we're actually going for a shrink. So the second generation chip is 7 nanometer process, and it is more than 2 times larger in terms of number of cores and in terms of available memory on the chip. So we are bringing up that second generation device in-house. And the first generation is right now being deployed in a number of customer sites. So this chip is quite unique. And yes, it draws quite significant amount of power, although that amount of power is comparable to what type of power you would draw to comparable compute for GPUs or for CPUs. But to be able to power and cool down that chip, we also built a system. We call it Cerebras CS-1. we package or we put a single wafer scale engine into single CS1, into single chassis. That system and this chip is programmable using standard machine learning frameworks. So you can write your code in TensorFlow, PyTorch, and then we have our graph compiler, which will compile that code and execute that directly on Cerebras wafer scale engine. It deploys into standard data center. It fits into standard rack, roughly a third of a rack, 15 standard rack units. And we have multiple deployments across the world these days. This system and the chip was built from ground up for AI acceleration. And we especially kind of thought about types of models which people train today and which we believe people will be training in the future. So let's take a step back and look at those models. I promised you a journey at deep learning. So here we go. We will start with computer vision just because deep learning became popular with computer vision, and the very first applications of deep learning became successful in computer vision. So deep learning in computer vision has the longest history, and I think that field is much more mature than applications of deep learning in other domains. And probably we will see yet similar trends which we see today in computer vision in other domains as well. So what I've tried to do here is to kind of plot different models. I took ImageNet as one of their well-known benchmarks for computer vision models. Not widely used anymore because the images are not that big and the task is not that challenging anymore. But still, when you introduce a new model, people sometimes test that on ImageNet. And it was the only benchmark available a few years back, so it allows you to compare models of the past and models of today. So what we look here is at top 5 accuracy. It's a classification benchmark. So the top 5 accuracy tells you if you get right, if you classify it right, like top 5 things in what are the top 5 answers, or what are top 5 labels to your image, and if you get at least one of them right. And then we also look at sizes of the models, which are represented by the size of the bubbles. And I try to kind of let you know the exact size by those labels. So this represents the size of the model in millions of parameters. And as we can see over the time, the accuracy steadily improves. So we are now very close to 99.7% of accuracy for the latest models. Model sizes also grows, but they grow very gradually. So we came from 60 million parameters to roughly like 50 million parameters of today, and you can also see that they oscillate. So for example, here this model is much smaller than it was the predecessor, but it still shows much higher accuracy. So let me show you some of those models. So the very first one is AlexNet, and the very well-known winner of ImageNet challenge in 2012, and which showed a tremendous progress on that benchmark compared to traditional computer vision algorithms, which I now question myself if I should teach students those or not. Then the next year, there was another contender also based on deep neural networks, winning the ImageNet competition. Then we have VGG19 and Inception models, which probably you've heard about if you looked into deep learning. What's interesting again here that this Inception model is much smaller compared to previous years, models of the previous years, and compared to VGG19. But still, although it's not as performing as a larger VGG19, it outperforms models of the previous years. And then the trend kind of continues to grow. So we have a family of ResNets, the most accurate being the deepest ResNets build, 152 layers, and with the smallest one being ResNet, I think that was ResNet 34 here, with 11.2 million parameters. And then we'll go to combination of different ideas, so combining Inception with ResNet. And there are also first attempts to kind of make those models smaller so they can be deployed on mobile devices. And although we use in accuracy, there is still research going on, active research, how to make those models more tangible to run on compute devices which don't have as much compute and don't have as much memory as the BPS GPUs. So I think the trend when you see here that the models size goes up is also kind of attribute to better hardware available to us, more memory, more compute available of that hardware. So researchers try out larger and larger models, but still they also look at the ways how to kind of condense those models and how to make smaller models work. And what's interesting here, like we see that alongside with very large circles here, we continue to have very small ones, and people continue to train successfully smaller models with them over the time. Every winner here at every year is still the largest model built, but the difference between the largest model and the models which are much, much smaller is not that huge. And also they've had their change of model from like 60 million to something like 50 million over 8 years doesn't seem to be as drastic. So now let's look at natural language processing, which becomes more and more popular these days, and where the picture is slightly different. So we'll also look at kind of quality versus model size plot. Here I am showing perplexity on a Wikitext 103 data set, which tells you the quality of the language model. So essentially how well the model can predict next character or next piece of word when it's generate text on its own. So how well it understands the properties of the language. And you can see that there is a very clear trend here. So when we look at models of different sizes, which been proposed over the past maybe couple of years, natural language processing is much, much younger. Not language applications of deep learning in natural language processing became much, much more popular in recent couple of years with the ability and discovery to do this self-supervised pre-training and pre-train those models on unlabeled data. So we see that the quality of models improves linearly with the model size growing exponentially. So the scale on the horizontal line here is logarithmic. And we also see that the size of those models becomes extreme. So we started from like a little bit below 100 million parameters. And right now, like just a couple of days ago, Microsoft has published a blog mentioning that they now figured out how to train 1 trillion parameter model. So the growth of the models is much, much larger than you've seen in computer vision, mostly due to the fact that in natural language processing using this unsupervised or self-supervised pre-training, you can train that on very large corpora of data. And if you train on large corpora of data, you can increase the model capacity, you can increase number of parameters, and those models tend to perform better. It's not only about the quality of the model itself. You might say, okay, what would I do with the language, natural language model? Yes, I can probably generate the text, but what else? If you translate that to the, some names of the model so you know what I'm talking about. Here we kind of travel from their some early LSTMs and transformers to BERT, large, GPT-2 and GPT-3 proposed by OpenAI. This one is a very recent thing they published in June, a paper on GPT-3 model, which caused quite a resonance in scientific community because it's the first model which was able, after pre-trained, do quite well on downstream tasks to do things like answer questions or predict some answer, like in an open form, tell you their modality of the sentiment without additional fine-tuning. So essentially, you don't need any labeled data. You just pre-trained it on unlabeled data, and then you can force the model to also answer their downstream tasks, which are typically fine-tuned with labeled data. And again, the size of the models continue to grow even after that. So looking at one of their downstream tasks, here I picked sentiment analysis when the goal is to predict the polarity of the sentiment. So if users are happy or unhappy with some product, or if some review in the movie is positive or negative. So the models on these downstream tasks can be fine-tuned from after they are pre-trained on unsupervised text. So you first train a very general language model, and then you can adapt that, you can fine tune that with a very small amount of label data to a specific downstream task, like in this case, into sentiment analysis. So we can see that here there is a similar trend as with just quality of language models. The larger means better. Larger models we train, better they perform on downstream tasks. And also to give you an idea what kind of models I'm talking about here, we start our journey from Tiny Bird, which is an attempt to, again, squeeze down their BERT larger models. So essentially, if you look in history, those BERT models were introduced first. You see they have size of 110 million parameters, 340 million parameters, and Tiny Bird is an attempt to find the structure of the smaller models, but which will still perform as well. And they've done pretty good considering the size of the model. But there is also still kind of a chase towards larger and larger models. Here I have results only on Google's T5 models with 3 billion parameters and 11 billion parameters on this data set. But there are also, like as I mentioned, attempts to train even larger models here. Another interesting kind of a couple of outliers, also Albert and ExcelNet. These are also examples of models when the people try to look at algorithmic innovations, and when they try to kind of reduce either the memory footprint of the model or the computational demands of the model in order to get to better quality but at low training time. So these are examples, so these are improvements, these are proves that improvements in the models are possible not only because of the size, but improvements in quality of the model also possible with some algorithmic innovations when you do things differently. I think here we kind of see the similar turn as we've seen in computer vision when after kind of when people try to see how you can make smaller models work well. So I've talked a bit that natural language processing model, NLP models are much larger. Let's look at essentially how much larger, how much memory you would need for those, and how much compute you would need for those. But again, here is another plot. We look at a relation between model memory requirement in gigabytes, and that's just part of the memory which you would use when you train a model. So part of the memory on your device will be used to just host the model. Their estimates here are made assuming that you're training with the Adam optimizer, and you do that at mixed precision. So that typically results in roughly 16 bytes per model parameter in memory requirement, just to host your parameters of the model, just to host the gradients and optimizer states. And also the requirements in compute. I'm here adapting the metric introduced by OpenAI, petaflop days. So essentially, that's if you have an ability to sustain petaflop per second, so you have a hardware which is capable to give you petaflops per second compute, how many days it will take you to train your model with that compute. And I think it's very convenient to think that 1 petaflop a day is roughly about running or utilizing at 50% DGX to H or like 30-40% DGX A100. So in my mind, it's easy to say that it's easy to think, it's easy to translate that this kind of petaflop days translates to kind of number of DGX days to train a model. So some of the models here, again, starting from BERT base and BERT large. So one of the first models where the idea of this unsupervised pre-training was introduced. Then going to OpenAI GPT-2, which is 1.5 billion parameters. Then NVIDIA trained this Megatron LM, 8.3 billion parameters. Google's versions of 11 billion parameter model. Microsoft's 17 billion parameter Turing NLG model. GPT-3, 175 billion parameters. And recently posted information about Microsoft 1 trillion parameter model. So if you look at memory requirements, we start from 2 gigabytes, which is decent, up to 16 terabytes. So 16 terabytes obviously is insane. But good news that when we talk about memory footprint, there are tweaks how you can reduce that memory footprint. And yes, that's memory only for model. You still need to account memory for activations. The activation size and natural language processing are not as large. So typically the memory requirement is dominates by model memory. But even the model memory, you can do some, because it's very compute intensive. So you can allow yourself to store some of the model parameters off the chip and bring the layers which are needed for the current computation when it is needed. So that's essentially what Microsoft did, because they trained that model on 800 GPUs, and 800 GPUs won't give you 16 terabytes of HBM. There is no other way to train a model that large. So model memory challenges, although annoying, they can be addressed. What about compute challenges and the compute requirements? For natural language processing models, their compute requirements grow linearly with the model size. And that means that as we try to train those larger and larger models, we need more and more compute. And according to some inference from open papers and blog posts, my guess is that something like NVIDIA Megatron model, which is 8 billion parameter models, it took them about maybe 10 days to train on 512 V100 GPUs, so it's 32 DGX to H's. And it costs, if you look at, like, say, Amazon prices, it will cost you about $125,000. Something like OpenAI GPT-3 has been trained on 64 DGX to H's, so it's more than 1,000 of GPUs. And they train that according, again, to estimates and based on information of kind of sustained flops, which they published in the paper. It should take them about 116 days. And it should cost them also, if they would pay the prices like everyone else, around $2.7 million. So the cost to train those models in terms of the infrastructure which you need, in terms of just paying for those processors is insane. And it's just the final run, but you always need to remember that before you start that final run, much more resources spent on figuring out what the right hyperparameters of the model, or figuring out what the right structure of the model. So a lot of resources spent on researching those models before, and then you are ready to launch your final run, which is very expensive on itself. So we believe that it's not sustainable, and the future path, yes, we've seen great promise of larger models, but those models should become smarter. This brute force scaling is very challenging. So we see increasing requirements for memory, we see increasing requirements for compute, and those requirements can grow beyond what hardware industry can provide. And I think even Cerebras' largest chip, if we just rely on dense computations, it's not enough to train those huge models. You will still have to cluster and build humongous clusters of our devices. We believe that we need to look much closer into algorithmic innovations and to build more efficient models. One tricky part is those algorithmic innovations, many of them are challenging for existing hardware, because the existing hardware GPUs, which we are using today to train those models, they are SIMD engines. So it's a single instruction, multiple data. That means that they rely on the ability to perform exactly the same instructions on multiple data points. And they are very well suited for dense computations. And I believe that the path towards those smarter models and the way how you can still keep the capacity of the model, so you can still train the model, which is large, but reduce their compute requirements, is by carefully choosing which model parameters you would update based on which input data points. So let me kind of demonstrate and walk you through some graphics to help you understand. So let's say we have a training data and we have multiple samples. Every sample is represented by a number of features. So you can think as one sample being a sequence of tokens if we're talking about natural language processing, or a sequence of pixels if we're talking about images, or sequence, I don't know, sensor measurements if we talk about time series sensor data. So essentially, we have these tensor of training samples. Every training sample could be a vector or could be a matrix on its own, but I draw it in 2 dimensions to make it easier. And we also have a body of model parameters, which I reproduce here as a matrix, but it could be like also multi-dimensional tensor. So in my picture here, at least it's very schematic. Assume that the kind of first columns here represents earlier layers of the model, and last layer represents last columns represents last layers or later layers, deeper layers of the model. So how we train those models today, or all of the models today, we essentially use information from every single feature of every single sample to update every single parameter in the model. So essentially, we are doing dense computations all the time. So what happens if, for example, different training samples have different amount of information? And for example, there are some ideas about models with the so-called dynamic depth, where you decide how many layers you should apply for a certain sample, so you get the representation of the data, which is the right one. And speaking about natural language processing, again, let's assume that my sample here is just a sentence. So it's a sequence of talking, sequence of character sequences, sequence of words. So what if my sentence is very simple? I don't know, something about dogs like food, or I don't know, like there is sun in the sky. So there is nothing ambiguous about that sentence, and that means that and there is nothing ambiguous about every kind of single word in that sentence. That probably means that I can arrive at a very meaningful representation of that sentence, of every talking in that sentence, with very few transformations. So I don't need to go through hundreds of layers of deep neural network to get that representation. So that means that I can cut the latest layer of the compute and just don't do that. But for another sentence, which could be very ambiguous and very complex, I may still want to go through all of those layers of transformations to get to the representation which is meaningful. Let's take one step further. What if I'm not interested in talking about sequence and sequences betas, but what if different tokens in the sequence, in my sentence, also are more or less ambiguous? So let's say the few tokens of the few words in the beginning of the sentence, the few words in the end of the sentence, again, are very simple. So we have some concepts which don't have double meanings, which are very easy to find the right representation in my high dimensional space of representations. Again, I can take just a couple of transformations and I'm already there. So I know what's the right mapping in this high dimensional representation space to my tokens, to my words. And some other words could be much more ambiguous. Again, in order to understand what's the exact meaning of those words, I will need to look at the context. I will need to go through multiple transformations to be able to distinguish that specific meaning of that word in a given context. So the amount of compute which I would apply towards those transformations is different. It's different for every token. And if we take this idea to extreme, I can say that every single feature of a sample, of a training sample, we may decide that we want to use that to update just a subset of the models in my model. And there are some ideas, so this dynamic depth, an idea of conditional computation along depth dimension, it's just one idea. There are also ideas about conditional computation which can be applied on the same level of depth. So the recent Google's model in natural language processing, which was using a mixture of experts, essentially exactly that. So you have a model which have multiple towers, and you decide which tower to execute depending on a given token, depending on a given sequence. So that means that not only I can decide how deep I would like to go for a particular token, for a particular sequence, but I can also decide which tower, which subset of the parameters which belong to the same layer I would like to execute for a given sample. And essentially what that means that I would like my hardware to support this very kind of dynamic sparsity. So I would like to on the fly understand which model parameters I would like to use to define the transformation of a given sample. And that's very hard to do with existing hardware. So that requires hardware which is not essentially SIMD engine. It requires the hardware which is capable to do different iterations and different data points. And that's exactly what we try to do with the wafer scale engine. So that chip has been designed for flexibility, has been designed for sparse linear algebra operations. So what do I mean by flexibility? By flexibility, I mean an ability of every single core to do different job. So we have on our chip an array of 2D mesh of 400,000 cores. Each of those cores can be independently programmable. So every single one of those can do different instructions on different data at every given cycle. And that gives us immense flexibility. So that's also a core has special instructions, special function units to support operations on tensors. It's optimized for doing essentially sparse linear algebra ops on tensors, on sparse tensors. The architecture of the chip is essentially Dataflow scheduling. We do Dataflow scheduling in hardware. What that means is that no operation is executed on a core without the data. Might trivial, but kind of the arrival of the data and the arrival of the control triggers the instruction lookup. So depending on where the data arrives from, we look up different instructions which are placed on the chip during the compilation time. And then that instruction being executed and non-zero elements are sent to neighbor processing elements, neighbor cores to continue their computations. So what that means is that we have kind of intrinsic ability to harvest sparsity. So the sender, if we get some zeros as a result of computation, we will never send those zeros onto the chip, so the fabric will only communicate non-zero elements. And as a result, another core, which is supposed to do the subsequent operation on the data, it will never receive zero data, and it will only compute on non-zero elements. And thanks to this data flow, essentially, when you have very sparse data, you can speed up things. And we have some synthetic experiments proving that the hardware has this intrinsic ability to harvest sparsity and to show significant speed up when you have sparsity in your data. So here I show the measurements from WISE, from wafer scale engine, and from a GPU. For a synthetic model, it's just a 34-layer fully connected model, which first we designed that to be completely dense and to use identity activation function. So that means that there is no sparsity at all, and essentially just a number of linear operations, 34 layers of matrix multiplication. And we normalize performance on both CS1 and GPU kind of on this dense case to 1. And then we start to add sparsity. First, we add some natural sparsity. So we replace identity activation function with the ReLU, which zeroes out all negative elements. So we do kind of matrix multiply, then you zero out all negative elements, do next matrix multiply, zero out non-zero element, negative elements, and so on and so forth. And since you kind of continue to progress towards deeper layers, less and less elements are non-zero. And wafer scale engine CS1 system can take advantage of that. So there is no change in programming, nothing. You just replace identity with ReLU, and you see you're like 1.6, 1.7 gain with ReLU, just because you're using activation function which introduce zeros. But then we can push that even further. So we also experiment with the kind of artificial induction of sparsity when we zero out a given percentage of the smallest by magnitude elements in activations. So after ReLU is applied, we just knock out 25% of kind of non-zeros. 25% of the smallest elements by magnitude. And we can also kind of dial that up to 50%, up to 75%. And we continue to see increase in speed on CS1. So essentially, this completely synthetic experiment proves that hardware is capable to take advantage of sparse data. What it means in real world, or what it means for some of the real models. In some of the models, like transformer model, which is used for machine translation, there is what we call natural sparsity. So transformer uses this ReLU activation function. It also uses dropout. So that means that kind of layer after layer, some activations will be zeroed out. And we can take advantage of that, and we can see acceleration when you train something like a transformer on CS1. So in those feed-forward layers, they actually structured. You have fully connected layer, which is in matrix multiply, ReLU fully connects and then drop out. And those ReLUs and dropouts, they are very sparse naturally. So just by running transformer with the like indicating that we want to harvest sparsity, we see 1.2 performance gain versus dense case. So that's for the models which have sparsity inside already. Some of the models like BERT, they don't have intrinsic sparsity, so that ReLU activation function in BERT has been replaced by GELU, which doesn't have that nice property to zero out all negative elements. But what we figure out is that in BERT model, you can actually induce sparsity. So using the same approach which we used in that synthetic experiment, we can induce sparsity on both forward and backward paths, so into activations and into deltas, which flow on a backpropagation. And we can get up to 1.5 performance gain with up to 50% sparsity with kind of no minimal accuracy loss. I think we can get up to 1.2, 1.3 without any accuracy loss. And if you increase the sparsity a little bit up, it goes a little bit, like we lose a little bit of accuracy. But then I think about this, that ML user has control on that trade-off. So ML user can decide how important for this, for him, speed versus accuracy. And although for researchers know that every single bit of performance is very important, it can mean if your paper accepted or not into the conference, if you're called the next state-of-the-art model or not. But in production, the reality is that sometimes this 1% in performance is not seen by end user. It depends on the application. For some applications like click-through rate prediction, every single fraction of the percent of improvement will translate directly to money. For some other applications, that's not the case. And it could be that for those applications, people can benefit an ability to train models faster at the expense of this small difference in accuracy. And there is also another comment on these. So these experiments we've been doing with the BERT-based BERT large models. So it's 110 million parameters, 300 million parameters. And we've seen that when you increase the model size, the models become much more forgiving for sparsity. So it's much harder to induce sparsity in BERT-based than it is in BERT large. Right now, we're also running experiments with larger models. And based on initial experiments, we believe that as you continue to grow the size of the model, it becomes kind of more and more forgiving to induce sparsity because the capacity of the model becomes larger and larger, and you can get away with those additional sparse elements in the model. So why our chip is good in dealing with something like that or take advantage of that and see those performance? Because it's designed to kind of unlock those smart techniques. And there are two key properties which enable us to those tricks with sparsity, the tricks with the conditional computation. The first property that wafer scale engine is a data flow architecture. So we have kind of flexibility to stream data token by token or pixel by pixel. So that means that we have a flexibility to do different operations on different data points. So that dynamic sparsity, which I showed a few slides back, can be implemented on CS1. And also due to that, we have kind of inherent capacity to harvest sparsity without no actions from the programmer, without no actions from the ML researcher. It will be just taken care by the hardware. And also wafer scale engine is a MIMD architecture, multiple instruction, multiple data. So again, every core can be programmed independently and can do different operations on different data points. And that's extremely important to enable techniques of these conditional computations, dynamic depths, or dynamic sparsity. Here are some examples of those techniques which people explore these days in attempt to reduce either memory footprint or computational load when you train those very large models. And you can see that most of those techniques actually target the reduction of compute. Because as I mentioned, reduction of memory, although important, there are possible ways how you can work around. And you can also trade memory for compute, at least for activations. So you can do things like using reversible layers. You can use checkpoints. So there is an ability to train memory for compute. So if you don't have enough memory, you can throw more compute, recompute some of the things, and you're good to go. but there is no way to trade kind of vice versa. And they've shown those models become kind of prohibitively expensive to train. So people look at the ways how to reduce compute. So the first line here is one of the modifications of BERT called Albert, which is essentially an idea that you can share weights across multiple layers of your deep neural network. So the model parameters are not unique across the layers, but you reuse the same weights as you go deep and deeper. So that technique obviously reduces memory footprint, because instead of keeping 24 layers of parameters, you keep only one, or if you like, depending on the degree of your reuse. But that also means that the amount of compute goes up. Why so? Because you still want your model to have some capacity. So typically for a model like Albert, when you use these reused weights, you tend to make those models wider. So although you don't have 24 layers anymore, 24 worth of weights anymore, you have only one copy, but that copy becomes wider. So the matrices becomes larger, and that increases the requirement in compute to train the model. So every single forward pass and backward path becomes more expensive. And this technique is very well suited for both traditional SIMD engines and to CS1. We all can benefit from lower memory requirements. But the rest of the techniques are addressing compute requirement. And dynamic depths, I've talked about this a bit. So you can think about dynamic depths being applied per kind of different granularity. You can think about dynamic depths being applied per batch of data. So when I try to decide how many transformation I should do for a particular batch of data, which is not very flexible, because in a batch I still can have very heterogeneous data, and it's very hard to understand what's the optimal number of operations for the whole batch of data. We can go into finer granularity and do that per sequence, but we can go then in the finest granularity and do that per token. And the amount of kind of floating point operation, the algorithmic complexity of the model will continue to reduce as you increase the granularity of this dynamic depth mechanism. And we are running some first experiments on CS1 with dynamic depth experiments, and see some improvements in speed. Sparsity, either in activation sparsity using things like ReLU or dropouts, allows us to reduce also the amount of compute. Sparsity in attention mechanisms, so for example, in sparse transformers, OpenAI showed that you can allow yourself to train models on a much longer context with much longer sequences using sparse attention. And it's also hard to support on SIMD engines efficiently, especially when those sparsity patterns becomes not block-wise, like right now in sparse transformers. But when you think about those sparsity patterns becomes more fine-grained. An example there would be something like graph attention neural networks, where essentially you need to do operations with adjacency matrices, which are very sparse, and the sparsity patterns there are completely kind of random. They are not blockwise like in attention sparsity and sparse transformers. So that will be more and more challenging for SIMD engines to harvest. And the last example here is instead, when you have irregular models, model shape or block shapes instead of a nice hand-designed models. So typically those you can see those when you use something like neural architecture search. An example of that would be a Volt transformer, or in natural language processing, or something like AmoebaNet in computer vision. So when people run neural architecture search, will allow some evolution algorithms to figure out what's the best topology of the model. And the outcome of that search is typically that every single layer of the model is not like the previous ones. So the layers are very heterogeneous. The tensors are of very weird shapes. You will have very thin and very fat tensors. And to kind of do operations on those tensors of irregular shapes is also might be challenging on SIMD engines, because they like things kind of square and nicely shaped. So kind of in summary, we know that we need larger, but I think what's more important, we need smarter models, because I don't think it's sustainable to train a dense trillion parameter model. actually did an estimate based on this Microsoft blog post, and think that in order to train that trillion parameter model on, I think they showed that they used 800 GPUs to run that. It will take them years to train that model if you use the kind of the same corpora as is used today to train GPT-3. So it's still not feasible. It's a huge engineering achievement, just an ability to show that you can run and nothing breaks. So you can fit everything in memory. You can offload what's not needed from GPU memory to CPU host, and you can distribute the model as big across essentially not as large number of GPUs, but it's still prohibitive to train it to convergence. So we need those models to become smarter. We need to rely on those dynamic sparsity techniques and to reduce the computational complexity of the models. And in order to do so, we need powerful and flexible hardware. So we need the hardware where when you reduce algorithmic complexity of the model, the speed of training goes down. The speed of training goes up so that wall clock time goes down. And unfortunately, we've seen the engines sometimes, even if you introduce techniques which reduce algorithmic complexity of the model, it doesn't result in shorter training time, just because the hardware is not capable to do those fine-grained computation. So it's Cerebras with a special purpose chip, and we hope that it will enable some of the ideas which I talked about today. So it is a very powerful single node because we have so many cores on a single chip. So essentially we have performance of a cluster, but ease of use of a single device. So instead of distributing your training across number of GPU machines, you can train it on a single device and you program that as a single device. So you don't need to care about different ranks, MPIs, and whatever to synchronize the work across multiple systems. It's very straightforward for a ML researcher just to leverage all 400,000 cores and get the speed without the headaches of distributed training. But also very flexible and dynamic. So it enables this fine-grained sparsity. It enables these conditional and dynamic ML techniques. And we see just a very kind of beginning of ideas where models become much more efficient. And we hope that our device will help to drive the field into kind of less dense, more sparse models and less compute intensive. So we're keen to see what are new ideas researchers come up with, which can leverage this hardware. So we hope that, we believe that still AI ideas will be shaped by the hardware which you have at hands. So we hope that there will be new models proposed which are really well suited for CS1. And I think I'm personally very excited by our collaboration with Pittsburgh Supercomputing Center together with Hewlett-Packard Enterprise and Cerebras. We are building an neocortex system which couples together two CS1s and one super-complex system. And what is even more exciting is that Pittsburgh is giving that system, making this system available for the academia at no fee. So if you're a researcher and interested and would like to see what kind of, like to try out some of the new ideas of those models, please check out Neocortex Early User Program. It will be fun to try to do something together on CS1. Thank you.
Thank you very much, Natalia. We have some time for questions. If you have questions, please pose them using Q&A, not using chat. And by the time you type in the questions, I have a question for you, Natalia. Have you explored how does your system scale as you do clustering? Because I mean, you can, in theory, cluster any other things like TPUs and others. And if you don't mind, stop sharing unless you want to share something.
No.
So that people can see you as you answer.
Yes. Yeah, so we start experiments with distributed training across CS1s. We are looking first at kind of model parallel training. The reason of that is because our compiler essentially allows you today to run, the default mode of execution is model parallel when you place all the layers on the fabric. And right now we can't tell the compiler like how much core, so which area it can use for a specific model. So it's quite straightforward to reuse that and to place the model not on a single CS1, but on multiple CS1s. But that work is still kind of in early stages. So so far, I think based on early findings and early estimates, we believe at linear scaling. We working on it.
And so that's in terms of performance. What about the cost? Because you can also put a number of TPUs or number of GPUs to come up with a similar performance, but they may be at the higher cost. So have you done cost analysis as well?
So we don't disclose cost publicly, but essentially our chip is equivalent in performance to a cluster, and it's equivalent at cost to a cluster.
Okay. So I have one question here from Rahul Kumar. How do you see the future of FPGAs for AI?
Yeah, so I think FPGAs are a great engine for for inference. The challenge with FPGAs is also that it takes time to program them, though they're not as flexible as like CPUs or some other engines. So I think for some specific applications, when you already know what the model would look like, and like FPGAs are a great example, and I know that they are used in some applications to accelerate search and to do very fast inference for some low power use cases. But I think in order to enable large scale training, I don't think that GPUs are a feasible choice.
Okay. So again, please ask the questions in Q&A window here. I have another question for you. And this is more general, not specific to this, but it's along the lines of the previous question. As AI is being deployed more in everyday's life, there will be more and more need for real-time responses, for example, in car, autonomous vehicles, etc. So do you see any trends as of recently for going in that direction? So because it takes a lot of time to do inference and
Yeah.
training as well, because...
Yes, I think inference in a sense it's an easier task than training because you don't have as many moving parts. So everything is static. The compute graph is static, and I think there are many good results on how you can shrink your model after it has been trained. So there are techniques how you can prune parts of the graph. There are techniques how you can end up doing much memory, but also much more compute intensive. So I think that today, the very large model at the beginning, then you shrink it for inference so that you can deploy on very low power devices. I think it will continue to be so.
I guess that is related to the next question that I think you partially answered. IoT devices might need smaller models as well while interacting with bigger connected models. Which are suitable models for these systems? It's a little bit more complex question. We have bigger and smaller, and which are suitable models for these types of deployments?
So as I said, there are multiple ideas how you can shrink those models, how you can use a larger model, since in the teacher role, and a smaller model in the student role, and you can, like, once you have a very large model trained and performing well, you can find ways to find a smaller model which will be as performant or almost as performant as a larger one, and you can deploy that one.
Okay, thank you. That was a question by Abhilash G. And then we have a question from Herman Gomez. Natalia, could you please comment on the power requirements of WSC technology?
Yeah, so CS1 draws roughly 20 kilowatts of power. That's cheap plus everything around that. Essentially, it's more or less equivalent of what you would draw in a rack of high power equipment, like rack of GPUs.
Okay, I think these are all questions, and we also ran out of time. It's 8:31. I'm very respectful of a lot of people, including Natalia, who have to go to work, even if that means going to another room nowadays. So thank you very much, Natalia. Highly appreciate this. Talk was recorded, and it will appear in the YouTube playlist that was announced. The address was announced as a part of the invitation to this call, but if you can't find it, just email me. Thanks again, everyone. Bye.
Thank you. Bye, everyone.